Hi everyone. Today I'm very glad to do a presentation for teaching outline to introduce the Truss structure to students incorporating hand calculation, computational assistive techniques, and lab sessions. Now let's start. Trusses are everywhere. They are used in bridges, cranes, even in parts of the International Space Station. And for good reason, they allow us to create strong structures while using materials in a very efficient and cost-effective way. So today I will talk about the fundamentals of truss structures and the methods for calculating. So what exactly is a truss? According to the first atom, a truss is a structure composed of members fastened together in such a way to resist change in shape and its rigid structures. The base shape of a truss is three members connected to form a triangle. Please see the first figure. If a load is applied, the angles of the triangle won't be able to change if the length of each of the members stays the same. This means that the triangle is a very stable shape which won't deform when loads are applied to it. And so it's a great base from which to build a larger structure. Take a look at this bridge, for example. The loads are transmitted from the horizontal floor beams to the two vertical trusses on each side of the bridge. Each of these trusses only carries loads acting in its plane, so we can analyze it as a two-dimensional structure. There are two important assumptions we need to be able to make for a structure to be considered as a truss. First, we need to be able to assume that all of the joints in the structure can be taken as a pin connection. Look at the first picture, meaning that members are free to rotate at the joints. The second assumption we need to be able to make is that the loads are only ever applied at the joints of the truss. We never have loads acting in the middle of a member because all joints are pinned. The members cannot carry bending moments. They can only carry axial loads. This simplifies the truss structure analysis. For truss, each member is either in tension or in compression. These assumptions are what make truss different from a frame. Unlike trusses, frames don't necessarily have pinned joints. A frame can also have loads applied directly to its members. There are a lot of different ways to build a truss, such as roof truss and bridge truss. And there are many truss designs, and they are referred to by specific names. These different designs carry loads in different ways. So here's a summary for the roof truss and the bridge truss. To be able to design or analyze a truss, we need to be able to determine the force in each of its members. This allows us to check that the members can carry the loads without failing or gives us the information we need to select the best cross-section for each of the members. There are two main methods we can use to do this: the method of joints and the method of sections. For method of joints, firstly we draw a free body diagram showing all of the external loads acting on the truss. And then we use three equilibrium equations to calculate the reaction forces. Remember that we are calculating the forces acting at each joint, not the forces in the member. If a member is in tension, the internal forces will be acting to make the member longer. For every action, there's an equal and opposite direction, which means that a member in tension will be exerting a force on the joint, which is acting away from the joint. Please see the first figure. Of course, for members in compression, the force will be acting towards the joint. Then we can draw a free body diagram for every single joint and work through them one by one to solve the unknown forces acting at each joint. We solve the unknown forces using the equilibrium equations. Since all of the joints are pinned connections, there are no moments on the way and they need to consider equilibrium of the horizontal and the vertical force. One thing we should introduce is that there are three common support structure types used in the truss structure: the fixed support, pin support, and roller support. The reaction forces of the fixed support are horizontal and vertical forces and the moment. The reaction forces of the pin support are horizontal and vertical forces, and the reaction force of the roller support is a single force and away from the surface. So let's work through an example for slightly simpler truss. First, let's draw the free body diagram and determine the reaction forces using our three equilibrium equations. For joint C, it is a pin support consisting horizontal and vertical forces. For joint F, it is a roller support which has only vertical force. Taking equilibrium of the horizontal forces, the horizontal force at joint C must be equal to 0, because it's only force in the horizontal direction. Taking equilibrium of the vertical forces, the reaction forces at joint C and F must sum up to 6 kilonewtons. So the joint C is at a distance of 3 meters from joint D, and joint F is at a distance of 6 meters from joint D. So taking equilibrium of the moments acting about joint F, we can calculate that the reaction forces at joint C. Rc is equal to 40 kilonewton and Rf is equal to 20 kilonewton. Now let's determine the forces acting on each joint. Please see the figure. Since we don't know yet which members are in tension and which are in compression, so it's easiest to just assume that all of the members are in tension, and so we will draw internal forces as pointing away from each joint. So please see the figure. If we end up with negative values for these forces, it just means that we guessed wrong, and the member is actually in compression. Now we can work through each of the joints, starting with joint C. Firstly, applying equilibrium equation at the designed joint. Analyzing trusses involves a lot of resolving forces to different angles. So if you want to be good at it, if you are going to need to remember your trigonometry due to time limitation, you should revisit this part after lecture yourself. All we have to do is apply the equilibrium equations to determine the unknown forces at joint C. Taking equilibrium of the vertical forces, the 40 kilonewton reaction force must balance the vertical component of the force FAC. And so we can calculate FAC as minus 40 divided by taking equilibrium of the horizontal forces, we get that the force FCD must balance the horizontal component of the force FAC and is equal to 30 kilonewton. That's all of the forces acting on the joint C calculated. The force in each member is constant, and so we now also know the forces acting on the joints at the other ends of these two members. We can repeat this process for joint A. We can start by considering equilibrium of the vertical forces, which allow us to calculate the force FAD, and then we can consider equilibrium of the horizontal forces to calculate the FAB. When Then need to work through all of the remaining joints, joint D, E, F, and B, one by one. For joint D, we can start by considering equilibrium of the vertical forces, which allow us to calculate the force FBD. And then we can consider equilibrium of the horizontal force to calculate FDE. Alternatively, if we just need FDE, taking a moment about B, we can get FDE from the equilibrium. For joint E, we can start by considering equilibrium of the vertical forces, which allow us to calculate the force FEB. Then we can consider equilibrium of the horizontal forces to calculate FEF. One thing you will notice as you analyze trusses is that some members don't carry any loads at all. We call these zero force members, such as FEB and FEF. For joint F, we can start by considering equilibrium of the vertical forces, which allow us to calculate the force FFB, and then there's no horizontal forces. Finally, we apply equilibrium equations at joint B for checking, so it's done for method of joints. Here we introduce computational assistive techniques for helping us do the complex truss structural analysis. SUP 2000 is a powerful finite element structural analysis tool, and we can use the results in SUP 2000 to validate our hand calculation results. By incorporating FE analysis software, students can gain a deeper understanding of truss behavior, learn how to apply computational techniques to solve complex problems, and achieve various learning objectives. Here's how software can be used and its benefits. The first one is visualization and interactivity. Truss analysis software provides visualization of truss structures, allowing students to observe behavior and deformations in real time. The second one is virtual experience. Software enables students to conduct a virtual experience that would otherwise be challenging or time-consuming in a physical life settings. The third one is complex problem solving. Incorporating FE software in truss structure analysis enables students to solve complex problems efficiently. The fourth one is collaboration and feedback. Software tools can bring collaboration among students and teachers. The last one is exposure to industry tools. Many engineering companies use advanced software tools for structural analysis, so students can gain practical experience with industry standard software for future careers. So here's a detail for a simple example for tutorial. The first step is to build a new model in SUP 2000 and then draw the frame object, and then assign joint constraints and locus. Finally, we run the analysis to get the forces and stresses results. Now we have covered the method of joints. Let's look at the other method we can use to solve trusses, which is the method of sections. The first step is the same as the method of joints. We draw free body diagram and use the equilibrium equations to solve the reaction forces. Next, we make an imagination cut through the members of interest in our truss, and we can draw the internal forces in the cut members. The internal and external forces must be in equilibrium, and so we can apply the equilibrium equations to solve the internal forces. When choosing how to cut your truss, remember that we only have three equilibrium equations. If you cut through too many members, you will have too many unknowns and not enough equations. Normally, we choose the side that looks easier to solve because there are less forces. The method of section is best used when we have a truss which has a lot of members, but we are only interested in loading in a few specific members. Let's look at example. We need to determine the internal forces in these three members, BD, BE, and CE. Let's draw the free body diagram and apply the equilibrium equations to calculate the reaction forces. Firstly, this is symmetric truss and this is symmetric load. So for both suppose we have only two upward reactions. The horizontal reaction force at joint A is the force only acting in the horizontal direction, so it must be zero. By considering equilibrium of forces in the vertical direction and the equilibrium of the moments acting at about joint H, we can figure out that VA is equal to 200 kilonewton. Next, let's make our cut through the chosen members BD, BE, and CE. Draw the internal forces and consider the free body ABC to the left of the cut. See the figure on the right hand, like we did earlier for the method of joints. Now we will assume that all the unknown forces are tensile. So next we just need to apply the equilibrium equations. Let's start with FBD. To find FBD, take moments of the free body ABC about E. Please see this equation, where LE is the perpendicular distance of BD from E. LE can be obtained from this equation. So FBD can be calculated. Next, we just need to apply the equilibrium equations. Let's start with FBE. To find the FBE, take moments of the free body ABC about J. Please see this equation. JK can be obtained from this equation, so FBE is equal to this value. Finally, let's find the FCE. To find the FCE, take moments of the free body ABC about B. Please see this equation. And the FCE is equal to 200 kilonewton. So let's have a brief introduction for the lab sessions. A three-dimensional truss is tested under different loadings, and the load deflection and the internal member strengths are measured. From the latter, the internal member loads are determined. These latter derived results are compared to results from analysis using a two-dimensional model of the truss. Thus, comparison can be made between the model of the truss and the performance of the actual truss, and therefore some examination of the validity of some of the assumptions made in forming the model can be examined. So before every lab work, we should do risk analysis for every student's safety, especially notice injury from toppling carrying equipment. The performance of the lab work requires three parts. The work before coming to the lab is called pre-lab work. Work during the lab is in-lab work, and the work to be done after leaving the lab is post-lab work. The details for this lab work and equipment setup, procedures, and lab report will be introduced later. So thank you.